Welcome student, Power Electronics Lab. In this section, we are doing three-phase uncontrolled diode rectifier. From this experiment, learning outcomes, understanding the simulation of power electronic circuit in Simulink, understanding the power GI block for FFT analysis of the circuit simulated, understanding the hardware implementation of power electronic circuit, circuit diagram of three-phase uncontrolled diode rectifier and model waveform, MATLAB simulation implementation on R and RL load, input voltage 50 peak equal to 61.2 volts RMS and frequency 50. In the first circuit, R value is 100 ohms. In RL circuit, R is 100, L is 6 millihenries. MATLAB 19 years simulation blocks and paths. So using this path, you have to select your all the blocks. Now we'll do the simulation. For this, double click on MATLAB icon on desktop. Double click Simulink. In Simulink, double click on block model. Now you will get a model with untitled name. Save this one. Go to File, Save as EXP3. Save. Now you got an empty model with here. Now we want to select as a blank. Go to library browser. In power electronics, path is select first Simscape. Under Simscape electrical. Under this specialized power system. Under this fundamental. So in that power GI, power electronics, measurements, elements, electrical sources. First select power GI, select add to your model. Double click on power electronics, select diode, add to model. Select measurement, three-phase VI measurement, add to model. Current measurement, add to model. Voltage measurement, add to model. Select elements in this series RLC branch, add to model. Electrical sources, select three-phase source, add to model. You want select as a bus selector. In Simulink commonly used block, select bus selector, add to model. Now you need a scope and display. This will be available in sync. Select scope, add to model. Select display, add to model. Now you need a mean and RMS blocks. In control measurements, select measurement. In that mean, select add to model. Select RMS, add to model. Now we selected all the blocks. Now we'll separate all the blocks. So first select three-phase source. So in that phase-to-phase voltage is 61.2 volts as a RMS voltage and frequency is 50. Uncheck. Otherwise check place with zeros. Source resistance is 0, source inductance is 0, base voltage 0. Apply and OK. And the configuration, select star with neutral. Apply and OK. Now double click three-phase VI measurement, voltage measurement, select phase to phase. Apply OK. Now here you require as a 6 diodes. So this will rotate first. Place 6 diodes. Now you can give the names of the diodes. So this one is D1, D3, D5, D4, D6, D2. Now diode and a 2 terminal anode and cathode, like that 6 diodes also having anode and cathode. Now we'll make the connection D1 anode to D4 cathode, D3 anode to D6 cathode, D5 anode to D2 cathode. Now D1, D3, D5 all the cathode are joining. D1 to D3 cathodes, D5 cathode to D3 cathode, D4 anode to D6 anode, D2 anode to D6 anode. Now double click on series RLC branch. In that R is select as a branch type as R, resistance is 100 ohms, apply and OK. Now you can rotate Control plus R. Now we'll give the supply to voltage measurement. From A to anode and cathode joint, from B to D3, D6 anode and cathode joint point, C to D5 anode, D2 cathode. Now current measurement, positive terminal to all the cathodes joint point. Current measurement negative terminal to resistive one terminal, resistive other terminal to D4, D6, D2 anode point. Now this voltmeter measure across the load voltage. Now you can select one more bus selector. So connect D1 E terminal to one bus selector, second bus selector to D4 E terminal. Take one more scope, double click bus selector, remove unknown signal, select diode voltage, diode current. Now, and to increase the input terminal to scope, double click this scope, go to configuration properties, number of input to 4, layout 4, apply and OK. Now first we'll connect as a D1 anode voltage, D1 diode current, D4 diode voltage, D4 diode current. Here also double click the scope, go to configuration properties, number of input port to 4, layout, apply and OK. Now first one VABC, second is IABC, third is output voltage, fourth is output current, now from the output mean and RMS you required, so mean to output terminal, next mean current and RMS current, now this mean connected to output of current measurement terminal, RMS to current terminal. Now connect mean to display, RMS to display, mean to display, RMS to display. Now double click mean block, fundamental frequency 50, RMS fundamental 50, fundamental frequency 50, RMS block fundamental frequency 50, apply and OK. Now save your file. So your simulation time is 10 seconds, so you have to give as a 0.5 second. Now we can label it also mean current, RMS current, mean voltage, RMS voltage. Mean current, RMS current, mean voltage, RMS voltage. Then it is easily identified from the blocks. Here also you will give display also. Now run your simulation by pressing run button. Now mean current is this much, RMS current, mean voltage, RMS voltage. Now we will see the input and output voltage and currents in the scope. Double click the scope. Now we can label this waveforms as a input voltage, now second one is input current. Right click on the graph, configuration properties, in the signal label change it. Input current. And okay. Now third one is the output voltage across the load. Output voltage. And okay. Now fourth is output current. And okay. Now you can easily identify which waveform is. First is the input voltage, input current, output voltage and output current. Now this we will take as a screenshot and save in the folder. Now we'll do FFT analysis on the output voltage as a R load. For this, go to configuration properties, logging, check log data to workspace, save format, structure with time, apply and OK. Close this group. Go to model configuration parameters, select data import and export, uncheck single simulation output, apply and OK. Again save your model, run your simulation by pressing run button. Now to open FFT analysis, for this double click Power GI, Tools, FFT analysis. Now select as a input 3 as a output voltage. Now fundamental frequency as a, we are doing as a FFT analysis of output voltage. Now fundamental frequency is 300 Hz. Display style, select as a relative list relative to fundamental and display. Now here you can maximum frequency change it to 10,000, you will get more harmonics. Now at fundamental is 300 Hz. Now DC component is 80.96, fundamental 4.69 peak, in that 3.316 RMS, THD 26.38%, when it is in fundamental 100%. Now we want to calculate second harmonic, select as a 600 Hz, the percentage 23.12, when it is in 100% you got in these values. Now second harmonic, your percentage is 23.12. Calculating according to this percentage. Now you have to calculate as a third harmonic. Select 300 Hz. Percentage is 10.97. For 10.97 percentage, how much DC component and how much RMS it is coming. Now you can calculate it. Now this also you can take a screenshot by using snipping tool. Save in the folder. Now we'll see the D1 and D4 diode voltages, diode currents. Double click the scope. First one and second one, D1 diode voltage, D1 diode current. 3 and 4 diode 4, diode fourth diode, diode voltage, diode current. This also take a screenshot, save in the folder. Now you can take a screenshot of your circuit diagram of simulation circuit. This one also save in the folder. Now we'll do as a RL load. In branch type, select as a RL. L value is 6 millihenries. Apply and OK. Save your file. Run your simulation by pressing run button. Now double click the scope. Now input voltage, input current, output voltage, output current. Now this output across the R and L. Now this also will do as a FFT analysis. For this, go to configuration properties, logging, check data to workspace, save format, structure with time. OK. Double click Power GI. Go to tools, FFT analysis. Input 3 is as a output voltage across the load. Now fundamental frequency 300. Display style is list related to fundamental and display. Now at 300 Hz fundamental. Now DC component is 80.95. Fundamental 4.678 peak in that 3.308 RMS. THD total harmonic distortion 25.49%. This is for when in fundamental frequency. Now second harmonics percentage 22.58%. When it is 100%, we got these values. When 22.58%, according to you have to calculate these values. Now third harmonic at 900 Hz, the percentage 10.58. Calculate these values at this percentage. Take a screenshot of this one and save in the folder. Now you saved all the files in the folder, result files. You have to attach all the screenshot of this in the result files as a R load and RL load. Hardware implementation on R and RL load. For this, power module is required. Second one, SCR diode power module. In the first case, we are using R load. In second case, R and RL load. Hardware on three-phase uncontrolled rectifier. For this, equipment required as one is power module. Second is SCR diode power module. Third is resistive load. Fourth as inductive load. Fifth is digital storage oscilloscope. With this digital storage oscilloscope will measure the output voltage and input voltage also. In the power module will give three-phase supply, single phase supply, DC supply. In our experiment, we required as a three-phase supply. So from the three-phase supply to input of the MCB, from the output to, in the three-phase circuit, 6 diodes required: D1, D3, D5, D4, D6, D2. In first case, resistive load, select as a resistive load. Across the R load, will measure the output voltage. Now we will make the connection with the help of BNC connector. Now from the three-phase supply to R2, R2R, Y to Y, B to B. This is three-phase supply to input of the MCB, SCR diode power module input side. From the output R, Y, B. Now first we'll select as a diode D1, D3, D5, D1 cathode to D4 anode, D3 cathode to D6 anode, D5 cathode to D2 anode. D1 and D4 anode cathode joining point to R phase, D3, D6 anode and cathodic joining point to Y phase, D5 cathode, D2 anode joining point to B phase. D1 anode, D3 anode join from D5 anode to D3 anode to join. D4 cathode to D6 cathode, D2 cathode to D6 cathode. Where the D4, D6, D2 cathode joining point to load one terminal, and D1, D3, D5 anode joining point to load other terminal. Now the probe terminal is connected at 100 terminal and probe negative is connected at 0 terminal. Between black and red, the resistance value is 100. This is a positive probe terminal. This is as a negative probe terminal. Now we will make circuit on. For this, switch on main three-phase supply, switch on meter switch, switch on main power module MCB, switch on three-phase AC voltage source, switch on SCR diode power module, and slowly increase voltage to 61.2 RMS voltage. Now adjust the voltage to 61.2. Okay, this current will call as a input side current. Now here unable to see, so now we can adjust the voltage division knob to increase the voltage division. Now you got an output across the R load, and from this you will measure as a mean and RMS value. For this, press measurement button. From this you can find the RMS voltage, mean voltage, and frequency. Now output frequency as a 300 Hz. Now these waveform you have to capture in the PC. Open choice desktop, open and select instrument, select USB, OK, and get screen. Now we got an output voltage across the R load, RMS voltage, mean voltage, frequency as a 300 Hz. Output voltage frequency is 300 Hz. That is nothing but your fundamental frequency of output voltage is 300 Hz. These waveform you have to save by pressing save as button. You can save in the MATLAB folder in the result folder. Open result folder and save some file name. I am giving some ZZZ. You can give some file name also. Like that you have to save the waveform. These waveform will do as a FFT analysis. Press mass function and press cursor button. Already cursor is placed at 300 Hz. Now we can adjust the cursor to fundamental frequency as a 300 Hz. At fundamental 300 Hz is the dB value is 10.6 dB. This value you can convert into V fundamental RMS. This FFT waveform also you have to capture in the PC. Open choice desktop, select instrument, select USB, OK, and get screen. Now you can observe the cursor one at 300 Hz, the dB value is 10.6 dB. This one also you can save in the result folder. Now we'll do this output voltage at second harmonic as a 600 Hz. Move the cursor to 600 Hz. At 600 Hz, the dB value is 990 milli dB, or sometimes it is varying minus 1.79 dB. These value convert into V fundamental RMS at second harmonic. Now we'll move the cursor to 900 Hz as a third harmonic. At 900 Hz, the dB value is minus 9.79 dB. This value you can convert into V fundamental RMS. Actually, we are observing three different fundamental frequency, but in that we are capturing only one fundamental frequency is sufficient to attach in the result file. Now we will do as a RL circuit. For this, make it of your MCB of SCR diode power module and remove one of the load terminal. Connect from another load terminal to inductance terminal and inductor other terminal to all the anodes are joining point. Now the probe also connected between R and L load. R starting point as a positive terminal, L ending point as a negative. This is a negative probe terminal. Now we'll make it on your circuit and voltage adjust to 61.2 and press channel 1. Now the output voltage across R and L load. Now from this waveform you will measure the mean and RMS voltages. For this, press measurement button and after pressing this DSO will be displayed RMS and mean frequency, output voltage frequency as a 300 Hz. This waveform you have to capture in the PC. Open choice desktop, select instrument, select USB, OK, and get screen. Now this output voltage across R and L load. These waveform also save in the folder. From the output voltage of RL load, we'll do as a FFT analysis. For this, press mass function, press cursor button and adjust the cursor to fundamental frequency as a 300 Hz. Now cursor one placed at 300 Hz. Now the value is dB value is 10.6 dB. This dB value you can convert into V fundamental RMS. Now we'll get as a V fundamental RMS at fundamental frequency. Now we want to capture this FFT analysis in the PC. Open the open choice desktop and select instrument, select USB, OK, and press get screen button. Now cursor 1 shows 300 Hz dB value. These waveform you have to save as in the folder. Now we'll do as a second harmonic. Adjust the cursor to 600 Hz. 600 Hz as a second harmonic. Now we got an 1.79 dB converted into V fundamental RMS. Now we'll calculate as a third harmonic. Adjust the cursor to 900 Hz. At 900 Hz, the dB value is minus 7.39 dB. This value will convert into V fundamental RMS. Now can calculate all these fundamental values as a equivalent value of RMS, V fundamental RMS. These values we have to tabulate in the tabular column, and we done as a three-phase uncontrolled diode rectifier with R and RL load. From this circuit again bring back to your original position, make it off your MCB of SCR diode power module and reduce the voltage to 0 volts and make it three-phase AC voltage to off and switch off your main three-phase supply. Results of R and RL load: attach waveforms of input voltage, input line current, output voltages, output currents, diode voltage of D1 and D4 in Simulink. Attach FFT list along with corresponding waveform for output voltage in Simulink. Attach waveform of output voltage FFT plot of fundamental frequency at 300 Hz experimentally from DSO. Attach the circuit diagram of three-phase diode bridge rectifier with R load in Simulink. Observation of R and RL load. Calculation performance parameters in Simulink. Observation of R and RL load. Calculation performance parameter of experimentally. Thank you.